Rank the following compounds in order of decreasing acidity. So we have structures of 3 different carbonyl-containing compounds to evaluate here. So first, let's interpret what the question is asking us. So it's asking us to rank the compounds in order of decreasing acidity. So what this means is we want to put them in order from the most acidic to the least acidic. And so we can evaluate this trend based on the structure, and we can also find the pKa values for these particular carbon acids in table 17.1 is where you will find these pKa values. And so I'm going to approach it by giving you the pKa values, but we're also going to take a look at the structures to see if we can explain it based on the structures themselves. So if we are using the pKa values though, the most acidic would be the one with the lowest pKa value. And then the least acidic would be the one with the highest pKa. And so if we are doing this based on the structure, we have this trend that we talked about in the first semester class, cardio. And this is giving us the relative order of importance that we should consider factors when deciding on acidity. So things like charge. Seeing a positive charge on something should draw your eye to it and maybe think about a hydrogen attached to that positively charged atom as being more acidic. We don't see any charges here, so that's not a factor. Atom is what atom that hydrogen is attached to. So we saw 2 things that affect acidity based on atom. We saw electronegativity and size. And in this case, all of the hydrogens in all 3 of these molecules are attached to carbon. So that's not going to be a factor. Then we get down to the next thing, resonance. This is going to be a factor. So what we're looking at here, and in all of chapter 17, that's why this is table 17.1, is alpha carbon acidity. So alpha to a carbonyl. So if you have a hydrogen, and we're just going to draw a nice simple ketone, so if we're looking at acetone, for instance, the hydrogen at that alpha carbon is more acidic than you would think, and that's because of resonance. So without considering resonance, you might say, okay, if we've got a regular alkane, so something like ethane, right, you're looking at a pKa value, depending on where you look, that's really high. Our textbook lists this as greater than 60, and so you can interpret that as not acidic at all, okay? But if you've got a hydrogen, so it's still an sp3 hybridized carbon, but if it's alpha to a carbonyl, once that hydrogen is removed by some base, it doesn't matter the base that we're talking about here, and so you can put that negative charge on the carbon atom. So what you would see, so this is now a CH2 minus, here's the resonance. So we don't have that negative charge localized on just carbon, we can share it with the electronegative oxygen. And this makes a big difference. Let me elongate this bond. So I want to be clear, like this arrow is going in here to the middle of the bond, because that's going to form a double bond, right? So we're able to share that charge with oxygen. So this is really a stabilizing factor. And so the pKa value for something like acetone, which is what I just drew, that has a pKa of 20. So this is an enormous difference that this resonance stabilization, and particularly resonance stabilization with something electronegative like oxygen, makes a big difference here. So the first structure here is a ketone like acetone, so we can approximate that pKa value again to be around 20. All right, and so if we look at the second structure, now we have an ester. So your first structure here, if we want to label it, this is a ketone, right? And our second structure, we have an ester. So what's different is what's on the other side of the carbonyl. So it's not these hydrogens that we're considering. It's the ones here where we can, if we remove it, it's going to be stabilized by resonance. So it's these hydrogens in particular that we're looking at. And so what we have is you would still have the same sort of resonance. You would just have a little bit less of it with an ester, because on the other side of the carbonyl, you've also got resonance with these pi, or with the electrons on the oxygen. So that means that this carbonyl is not as available to stabilize the negative charge as it is in a ketone. So if you're looking at the alpha hydrogens on an ester, you've got a pKa of about 25. So still a lot more acidic than an alkane, but not as acidic as the ester. And then finally, if we look at the third structure, we've got 3 different sets of hydrogens here. So we've got these ester hydrogens that we're not going to consider. So you've got an ester and you've got a ketone. And what's important about this structure is where these two are relative to each other. And it's the fact that you've got them at this 1-3 arrangement, 1, 2, 3. So that these hydrogens in the center are sandwiched between these 2 carbonyl groups. So these are your most acidic hydrogens in this molecule. And so if you get a negative charge there, you can share it between 2 carbonyls. And of course, the more delocalization you have, the better. And so you can take a look in this table for your exact pKa values. And here in between a ketone and an ester, so it's going to depend on which carbonyl compounds this is sandwiched in between, you're looking at a pKa somewhere in the ballpark of 10. So now we're talking about something that's fairly acidic. So what this means now, we just need to put these in order of decreasing acidity from most acidic to least acidic. So that means we're looking at this third one with that lowest pKa value being the most acidic. And that is more acidic than number 1, your ketone, which is more acidic in turn than your ester, number 2. So that means that B here is the correct answer for this problem.